Hopefully you've spent a little bit of time trying to think about what exactly all of these bits of the expression mean. So let me either confirm what you were thinking or perhaps guide your thinking in a more constructive way. The first thing that I should do is just introduce you to the name of this type of structure, because this is actually, as I mentioned in the previous video, a very common structure that you'll see in the higher levels of mathematics. This is called a sigma expression. Sigma is the name of this funky little symbol at the beginning of the expression. It kind of looks like a funky letter E, but it's actually a Greek capital letter S. And in Greek, the letter S is pronounced sigma. So while we say S, they say sigma, and it's their equivalent of a giant S. So if you want to see that written out, sigma is spelled S-I-G-M-A, and this is called sigma notation. Sigma notation is simply a way of writing a series of numbers in a condensed fashion. You can tell that 10, 15, 20, 25, 30 is kind of clunky looking. Like if you have to write it out, it takes you a few seconds to write it out. So sigma notation is kind of a condensed way of communicating all of the essential information about this series without having to individually write each term. Remember Gauss's problem from the previous lesson, the integers from 1 to 100? Nobody with a shred of common sense is going to ever write down every individual term in that series, 1 plus 2 plus 3 plus 4 plus all the way up to 100. So sigma notation can come in handy for problems like that in particular, because we wouldn't want to write out every individual term in the series. We don't even need every individual term in the series. And sigma notation is kind of a quick way of condensing it so that we don't have to write even the first few terms. We can just write this sigma notation and it stands for all of this at once. Now, in terms of the specifics of sigma notation, I hope that you kind of piggybacked off of a few things that you've already seen in previous lessons in this chapter thus far. The 5 plus 5n in particular was something that I had hoped would seem familiar to some of us. This 5 plus 5n hopefully looked to you like an arithmetic expression. 5 plus 5n kind of looks like the explicit equation that we would have written for a series that, or a sequence that has an initial value of 5 and an adder of 5, because we know that that has that arithmetic structure to it. The n as a regular size n, not an exponent, the plus sign, those are kind of hallmarks of a traditional arithmetic equation. So this 5 plus 5n really is the same arithmetic equation structure that we've known and loved before. This 5, for example, at the beginning, the one that does not have the n attached to it, is still to be known as the initial value of the sequence. And the 5 attached to the n, I'll kind of color code my writing here, the 5 attached to the n is always the adder of the sequence. And when you think about the numbers in the actual series itself, that kind of makes sense. And it might make more sense if you think of it in a tabular fashion. Tabular means tables, so I'll just quickly translate just for the sake of seeing it in a slightly different way. This sequence of numbers, or series of numbers, has a first term of 10, a second term of 15, a third term of 20, a fourth term of 25, and a fifth term of 30. This, of course, is the kind of traditional table that I was using in previous lessons, but the reasoning still stands true. The first number in the list is 10, thus first term, n equals 1. The second term in the list is 15, thus n equals 2, and so on and so forth. Now, of course, if this is the pattern, I know that tables work both forwards and backwards, so I can easily go backwards to predict what the initial value was, remembering that the initial value is always the 0 term in the sequence. And if I went backwards, the pattern simply involves subtracting 5, and that is the initial value to which I was referring in that sigma notation. So that 5, which I'll color code blue so you can see where I'm coming from here, that 5 is still the initial value of the sequence. Since the pattern still increased by 5 every time I jumped to a new number in the sequence, so that pattern of adding 5 is the adder, we've been calling it, That's why, with the green color coding, I wanted to make sure that connection is clear to the structure that we already know and love for traditional arithmetic equations. So a sigma really does kind of just reiterate what we already know about the arithmetic equation itself. The sigma's actual letter, the big fancy Greek capital letter S, is actually just kind of like a counter. The series itself, 5 plus 5n, could really go on forever. If you told me to keep this table going, I could keep going as far as I wanted to. I could go to n equals 6 and n equals 7 and n equals 8 and n equals 9. I could keep going all the way to 50 if I had the time. I could take this table all the way to the 100th term, the 10,000th term. I could even take the table backwards, n equals -1, -2, -3, -1,000, whatever I wanted to do. But sigma, this big fancy Greek letter S, is kind of like saying, whoa, 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 pump the brakes. Yeah, this is an infinitely long sequence of numbers. This is an infinitely long series of things that you can add. So I'm only going to ask you to focus on a few select terms. Remember that in that actual problem that we copied down from page page 9, number 5, part F, they only asked us to focus on terms 10, 15, 20, 25, and 30. Notice in my tabular format here what that means about the question or the sigma that you see. I only had to focus from the 10 to the 30. That was term 1 to term 5. The first term to the 5th term. N equals 1 all the way up to n equals 5. Do you notice something that's not quite just a coincidence about this sigma itself? N equals 1 is not coincidentally telling us to start at the first term in the table, the first term in the sequence. Sigma was actually telling me, hey, start with the first term. And then, just to make sure that you don't go on forever, because remember, you could start at 1 and go as far as you want to, sigma was saying, whoa, 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 pump the brakes, stop at term 5. So sigma is almost kind of like a little start-stop sign. Sigma tells you where to start counting the numbers in your sequence and where to stop counting the numbers in the sequence. It might seem counterintuitive that the starting number is at the bottom of the sigma and the stop number is at the top, but that's actually how we read a lot of Greek symbols like this. In fact, in calculus, we'll see another big fancy capital letter S with a very similar notation. So this is actually a little preview of what's to come for those of you going on to calc. We actually read all of these expressions from bottom up. So as weird and as counterintuitive as it might sound, you might be reading this instinctively from top down. Try to train yourself to read sigma from the bottom up. The bottom of sigma tells you what term to start with, and the top of sigma tells you what term to end with. So to just kind of make sure then that we understand what sigma notation is all about, let's see if we can make some sense of letter B, because here's another sigma expression. It says to consider this expression and prove that it's not equivalent to the one in number 5 letter F. Well, remember, the one in number 5 letter F is the one I copied at the top. This is saying that this sigma expression is not equivalent. Well, that sounds strange. Let me see if I can figure out why, because it looks like it would be the same. 5 plus 5n looks like the exact same arithmetic equation that I was dealing with. So I'm again going to translate this into familiar terms. I'm going to start with what I know about 5 plus 5n. I know that 5 plus 5n has an initial value of 5, and I know that the adder is 5, so 10 and 15, and so on. Now remember, I can build this table as long as I want to, so I'm going to look at my sigma expression to kind of get some guidelines. There's some boundaries here. This sigma is telling me to start at term 0. Okay, good, that's where I started. And it's telling me to keep going and stop at term 4. So term 0, term 1, term 2, term 3, term 4. That's how I know where to stop. So I'm going to keep the pattern going. 5, 10, 15, 20, 25. I'm going to stop there. So this sigma must have told me to use these numbers. This must be the series that they were talking about. 5, 10, 15, 20, and 25. Now, I'm looking at that, and I'm saying, oh, now I get what this problem was saying. Remember it said prove that this expression is not equivalent to the one from number 5, part F? That's actually a slightly different series of numbers. They have very similar patterns, of course, but this series starts with a 5. The previous series started with a 10. This series ends at 25. This series ends at 30. And if you actually found the sum, remember how on the previous page in number 5, part F, you found the sum? The sum was 100 when you did that problem in part F. If I add these up, 5 plus 10 is 15, plus 15 is 30, plus 20 is 50, plus 25 is 75. The sum of this thing is 75, not 100. So they're definitely not equivalent. It's literally a different series of numbers with an entirely different sum. So you can tell that the start and stop parts of the sigma are actually really important. Because if you start and stop sigma at different points in the sequence, you're going to end up with a very different sum. You're going to end up with very different values. And that, most importantly, is what sigma is so valuable to communicate to us. We know that sequences and series can go on infinitely, and it's that infinity aspect that makes sequences a little bit overwhelming. The idea of adding up an infinite series of numbers is basically impossible. Could you ever really stop adding? It seems like a futile task. So sigma is basically a way of saying, whoa, 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 pump the brakes. Let's not get carried away with ourselves. Let's just start at a certain point. Let's just end at a certain point. And let's just focus on a selected or finite set of numbers to add. If you may remember, when I initially described the formula that we were using, I was calling it Gauss's formula at the time. It was the formula from page 9. This is actually officially called the finite arithmetic series formula. And because it's a finite series, it has a starting number and an ending number. Or yesterday we were calling it a first and a last. That's what's helping us kind of define this notion that the series doesn't really go on forever. We have a distinct starting point and a distinct ending point. Thus, this series is finite. Finite just means it has a start and an end. It's the opposite or antonym of infinite. Infinite means it has no distinct start or end. So a finite series is one that has a beginning and an end, and sigma is just another way of communicating where to start and where to stop, including how to generate all the terms. So I'm going to have you skip letter C, just because it's not really the most important thing right now. If you want to challenge yourself with letter C, you definitely can. But I'm instead going to have you take a look at question number 7. Because in question number 7, I want you to practice seeing if you can parse this sigma notation for yourself. I'll do letter A as an example, but hopefully you can spend some time thinking about this and trying the rest of the questions on your own. Now, as kind of a start, especially if you're just seeing this sigma notation for the first time, this is barely your introduction to it, I would actually recommend using this tabular format and sticking with that as kind of a consistent way of making every problem look the same. If you don't want to use the table, it's totally understandable, but I personally find the table kind of helpful for visualization purposes, and you might want to do something similar. Now, when I'm looking at this series of terms, I know that these are the T of n terms, the 8, the 11, and so on and so forth. Since 8 is literally the first number they gave me, I'm going to call that n equals 1, because it's the first number, and first usually is 1. So term number 1 is 8, term number 2 is 11. It wants me to go up to 20, and just like I've seen in the past, it's not always clear how exactly or how many terms that's really supposed to be. So I'm just going to fill in the gaps because this looks like a pretty easy series to predict. 8 plus 3 is 11, so the adder must be 3. 11 plus 3 is 14, so the next term must be 3 more than that, that's 17, and the next term must be 3 more than that, that's 20. It wasn't super obvious from the question that there were supposed to be 5 terms in this thing, so that's why the table kind of helped me flesh that out. It helped me kind of visualize it. Now, let's think for a moment about what needs to go into this sigma expression. Now that I can see my table all laid out, I can tell that this series started with the first term, so n equals 1 must go at the bottom of my sigma expression. And this series ended at the 5th term, so at the top, I'll write a 5. Now, did you notice in question number 6 that we don't write n equals 5 at the top, that's actually just a small little mathematical notation that most mathematicians, or a convention that most mathematicians just kind of stick with. I mean, technically you could write n equals 5 up at the top of your sigma, but you actually don't have to. Most mathematicians just drop the n because at the bottom we're already establishing that those numbers on sigma signify n. So mathematicians just find it kind of redundant to put it on both the bottom and the top, and they just usually end up putting it on the bottom only. If you want to be consistent, you could put n equals 1 at the bottom and n equals 5 at the top, or you can put n equals 1 at the bottom and just a 5 at the top. It is important to put the n equals at the bottom though, because technically you have to tell sigma what your variable is. Some sigmas in future classes might have I equals or J equals, so technically it's a formality, but having that n equals there is kind of an important way of saying, hey, heads up, variable in this problem is going to be n, okay? And it's just kind of a way of sort of dictating that what you're writing in the parentheses is going to be in terms of n. Anyway, all that to say, it starts at 1, it ends at 5, we'll label our sigma accordingly. Now for the parentheses itself. The parentheses itself is where we write the traditional arithmetic equation, or the traditional arithmetic expression. A traditional arithmetic expression involves an initial value, which we need, and an adder, which we know. So let's go back for a second. We know that the adder is going to be 3, so we know for sure my expression is going to end with a plus 3n, because we know that it's adding by 3 each time. That's easy. The initial value is always the 0 term, which is not necessarily part of what sigma was specifying. That's not necessarily part of what we were given, but it is quickly and easily predictable. If I just go backwards one more term, even though I didn't really need it for the sigma, if I carry the pattern backwards, I can definitely predict that the initial value must have been 5, so 5 plus 3n must have been my arithmetic expression. That is a complete sigma. It tells you where to start and where to stop based on the given terms. Notice that the first given term was an 8, the last given term was a 20, and sigma told us to go from the first term to the 5th term. That would give us the 8 all the way up to the 20. It's telling us the equation that generates those terms, but specifically the importance of sigma is that it's telling us which selected terms to focus on, because we know that 5 plus 3n can go on forever and ever and ever. If I plugged 5 plus 3n into my calculator and looked at the table, I can definitely tell that that could be an infinitely long problem if I wanted it to be. So sigma is kind of a quick way of saying, no, don't go crazy. Just focus on the 8 to the 20. In other words, just focus on the first term to the 5th term, and you'll be good. So if you want to use a calculator to help you kind of visualize the rest of the numbers, you can. It's not necessary. It's just something to point out. The important part is just recognizing how to write your arithmetic expression using the same rules we've already used, and how to tell sigma where to start and stop. In between now and the time you start the next video, try to write some sigma expressions for letters B, C, and D. Try to get used to in what order you feel comfortable doing these things. Do you want to make a table? Can you predict things without making a table? Challenge yourself to try things in the way that suits you. You can use my example as a guide, but feel free to develop your own thoughts and your own style here. In between now and the time the next video, not only should you finish question number 7, but check your answers. Make sure using the answer key that everything makes sense. And once you feel like you've kind of got a handle on this, then we'll talk about what's left on the rest of the page.